Today we want to get some more calculus up in our calculus class, and we're going to start with partial derivatives. Remember that this question is going in partial derivatives. We're going to be adapting our old equation of the line tangent to a curve at a given point. We have updated that to the equation of a plane tangent to a surface at a given point. That's the new question. So new big question. I want to emphasize that there are 3 variables running around. This is a problem in R3. Here's our new big question. Oh, it's not even a question yet. Here we go. What is the equation of plane tangent to the surface? Z equals f of xy at the point x naught, y naught. What we're looking for is the equation of a plane. And the equation of a plane has a very predictable form. And we're going to write down the point slope. I guess it's a point and 2 slope form of the equation of a plane, the z equals version. When we're writing the equation of a plane, we need a couple of things. We need a place to start. And since we have a plane, not just a line, we're going to need 2 different slopes. I'm just going to call them M and N for now. So the shopping list for this equation of a plane is a point and 2 slopes. We need a slope M, which is going to be how z changes with respect to x. And N, which is how z changes with respect to y. We need a point and 2 slopes, dz dx and dz dy. We have to say dz dx and dz dy, or delta z over delta x. We don't get to say rise over run anymore because we have 2 directions of run. We've got x direction for run and y direction for run. So we have 2 different values for rise. So we've got to abandon our R and R definition. Conceptually, it's the same thing. We just have 2 different runs making 2 different rises because this is still a linear function and the rate of change is always constant in a given direction. We have used the word derivative, but they're called partial derivatives now. I also wrote delta z over delta x, and earlier I just straight up said dz dx. That's where our derivatives are going to show up. Those are the 2 partial derivatives, and we already know how to find partial derivatives. So you're looking at this and like, oh, if you're looking at this, this is going to be really easy. We already know how to do this problem. That is correct. We already know how to do this problem. We just have to adapt it. So the partial derivative part shows up exactly where we would predict it shows up. These are the partial derivatives. Not partial, partial. The owl. Remember, we write the D weird in partial derivatives.
Slanted D.
It's a slanted D, a backward 6. Or an upside down 9. Now, 9 upside down would be like what? U, I, U, and then upside, what's an upside down? A schwa. U, I, U, schwa. No, it's not going to work. Backward 6, X, I as this. No, it's not going to work either. We'll just say D. Other than that, this is an old problem. I'm going to give you part of a point. I'm going to give you 2/3 of a point, the X naught and the Y naught. You're going to plug those into the original function to find the Z naught. You're going to take 2 partial derivatives and plug in the points to find the 2 different slopes that we need. Put them together in the equation of a line. Let's start off with something simple like f of xy is, I'm going to go up higher. We go up to 9. If I go 9 minus x squared minus y squared, if I want to be a positive z, I have to pick x and y to be less than 3, and we'll be all right. So let's do y minus 9 minus x squared minus y squared at -1, 2. I guess there's not really a reason for me to cut this off at the xy plane, but oh well. So we know what this surface looks like. We're going to have a circular paraboloid. We see at the top, we're going to have a 9, and we're doing 9 minus a circle. So as x and y increase, x and y increase into a circle. We can see we start off with 9. That's just the top point. And then we just subtract circles. So 9 minus a circle. We want to look for these kinds of things so we can identify our circular paraboloids versus our hyperboloids. But the read I'm putting here is this is 9 minus x squared plus y squared. Those expressions are equivalent, but they speak to us differently. 9 minus circle, when we group the x squared and the y squared together. So let's find the equation of the plane tangent to this surface at the point -1, 2. So the -1, 2, that's our x naught and y naught. One of the things that we need for the equation of a plane is a place to start. So z naught will be f at x naught, y naught. So we plug in to find the point. 9 minus 1 minus 4 is 4. Now we've got a point. -1, 2, 4. We need 2 partial derivatives, a partial derivative of z with respect to x and a partial derivative of z with respect to y. Since I have written the function as f of xy, we need a version of prime notation. We can't say f prime at xy, because prime means derivative, but now we've got 2 derivatives. Prime ain't gonna cut it. So we need to separate a derivative with respect to x and a derivative with respect to y. Here's how we do it. The partial of f with respect to x has this notation. We write f, and we don't write prime. Prime is no good. We don't put an x up here. We decide to put the x as a subscript. So we say fx at xy. That's the prime notation for partial derivatives. And we just say it like it's written. Fx at xy. That's, we can't write prime because it's not specific enough. So we write fx at xy. And we say fx at xy. And we mean the partial derivative of f with respect to x. So we look at our function, x is the variable. What's fx at xy for this function? In this case, I see the 9 is a term. Remember, we have to separate between constant terms, constant factors. Derivative of a constant term is 0. Derivative of a constant factor, that just gets carried along. It's that constant times the derivative. The 9 is a constant term, so the derivative of 9 is 0. The derivative of minus x squared with respect to x is just minus 2x. The derivative of minus y squared is 0. Y squared doesn't have that term doesn't have any x in it, so it's not a variable term with respect to x. Y squared is a constant term with respect to x. Remember, think of the table. We're just looking at one row. We're looking at one row where the y is constant. So y is just some number. We're looking at the row where y is equal to 3. 3 is a bad choice. We're looking at the row where y is equal to 5. It's 9 minus x squared minus 25. It's just another constant. Because we're taking the derivative with respect to x. X is the variable. So there it is. The partial with respect to x is negative 2x. We wouldn't write the couple of zeros. We do need to know what the slope is at the point negative 1, 2. So we plug in the point negative 1, 2. So we're going to plug in for the point at the slope. In Leibniz notation, in case we need a reminder, if you put a vertical line, we'll say at negative 1, 2. Or in our prime notation, we just put the point in the parentheses. So if we want to evaluate Leibniz notation at a point, we just put the vertical line. Same kind of vertical line that we put after we do an integration. That just says evaluate this derivative at negative 1, 2. So that's going to be negative 2 times x, which in this case is negative 1. Now we want to do the same thing for partial with respect to y. Partial of f with respect to y, or fy at xy. The derivative of 9 is still 0, because 9 is still a constant term. Now our variable is y. So when we look at minus x squared is a constant term with respect to y. So the next is 0. Now we're just looking at one column in the table and looking at how y affects z. And then the derivative of minus y squared is minus 2y. Do the same thing. We're going to evaluate this partial derivative at the point -1, 2. And that will look the same. So partial at f with respect to y evaluated at -1, 2. Or fy at -1, 2. Is -2 times the y coordinate this time, 2. Now I've got all the things that I need to write the equation of a plane. I have a point and 2 slopes. And here's the function form of the equation of the tangent plane. We put this together in exactly the same way we put together the equation of the tangent line. We just had that other term with the other slope and the other coordinate. There's the points -1, 2, 4. There's the dz dx 2 and dz dy -4. So we can imagine this plane. The z value starts at 4, 1, 2, 3, 4 right here. The slope in the x direction is +2. The slope in the y direction is -4. I was about to try to draw it, but it never works out. So we're just going to have to use our imaginations. Imagination. How's that, okay? Easy, right? Because you already knew how to do it. I didn't even tell you how to find partial derivatives. Y'all just did that last week. I love it when math class writes itself. I don't know why people complain when movies are all predictable. I mean, what do you think was going to happen? I don't understand how people can complain that movies are predictable and then make the MCU, like that whole Infinity War thing, like such a big deal. Like billions upon billions of dollars we spend watching the MCU, and then we turn around and complain about other movies being predictable. Come on, man. Seriously? I remember a while before like Endgame and Infinity War, Mark Ruffalo was catching some shit because he was like, "Oh yeah, ha ha ha, we all die." He was like joking around because he was on a press junket, and that's what you have to do when you're in one of these movies. You're on the press junket. They joke around. It's like, "Oh, I think we all, probably all died." And it was like, "Oh my God, how could you say that?" I'm like, "Oh, we fucking know. We know what's going to happen. You have told us what Thanos' plan is. You told us what movies you're going to be making. You've got two, one called Infinity War and another one called Endgame. Gosh, I wonder what happens in those movies. I wonder if it's Thanos wins, then Thanos loses. It's a comic book movie. Death is not really important stakes. You know what I mean? What are we talking about? Oh yeah, predictability. Why it's easy to like the movies, because predictability is easy. Reacting is difficult. Metabolically speaking. So here's the equation of plane. Perfectly valid description, but there's more. There's more that's going on here. If we take the equation of this plane, we know we can describe it with two slopes like this. Slope in the x direction and a slope in the y direction. We know we can describe it with two slopes. We know we can describe a plane with two vectors in the plane. We also know that we can describe a plane with one vector normal to the plane. Let's find that normal vector to this plane. So if I rewrite this, let's see, just do a little algebra stuff here, plus 2x. I guess this is excessive, but I'm going to do it anyway. Plus 2 minus 4y plus 8. So I'm going to put the x over here. It's like a minus 2x plus 4y plus 1z is 4, and 2 is 6, and 8 is 14. Here's a slightly different description of the plane. This is the plane through 0, 0, 14. That's the z-intercept, 0, 0. Yeah, 0, 0, 14. That's the z-intercept of the plane. What we get from the standard equation of the plane is the normal vector. I didn't say the normal vector because there isn't the normal vector. This is just a normal vector. Now that we can identify this one vector being normal to the tangent plane at that surface, we can call this normal vector, this vector that's normal to the plane. We are also going to say that this vector is normal to the surface. We're going to say that this vector is normal to the surface. And when we say a vector is normal to a surface, when a surface is all curvy, we're saying it's normal to the plane tangent to the surface. But we're going to shorten all that, and we're just going to say that this vector is normal to the surface. So we also say this is the vector we would also say that this vector is normal to the surface at the point. A lot of times we'll say this is the slope of the function at the point. This is the equivalent of that. The function is all curvy and weird. When we say the slope the slope of the curve at the point, we're talking about the slope of the tangent to the curve. When we talk about normal to a surface, we're talking about normal to the tangent plane to the surface. That's just part of the language that we're going to be using. Another thing to note, this is our best linear approximation to the surface at this point, or near this point. Just like with the tangent line is the best linear approximation to a function near a point. So is the tangent plane. Tangent plane is going to be the best linear approximation to the surface near the point. All the stuff, what we did before, stuff that we're doing now. We just have to do partial derivatives to get there. Any questions? How's everybody okay? Everybody looks stunned. So the power went out, and so we didn't get to plug ourselves in and recharge. Wouldn't it be great if it just worked that way?
Not like you, but it's good.
Yeah, everything's all thrown off. Any questions? So what does this mean for us? This means we have to build a new skill set, which is really just adapting an old skill set. I have to be able to throw a function of two variables to you, and you have to be able to return two derivatives. Variation on the previous theme. Find me the two partial derivatives.
I assume that,
No point. I don't care about that. I don't have a point. I'm not trying to find equation of tangent line. I just want to find the first two partial derivatives.
right,
So I'll just be specific. Find zx and zy. Wrong order. So our read on this function for the partial with respect to x, 9 is a constant term with respect to x, derivative of 9 is 0. When we look at minus x squared y, that y, this y here, that y is included through multiplication. So that y is a constant factor with respect to x. Derivative of minus x squared is minus 2x times the constant y. The minus y squared, no x in that, so the minus y squared is a constant term with respect to x. Derivative is 0. So our partial with respect to x is just minus 2xy. So as far as zy, I kind of knew I didn't want that there, but it's fine. If our read on the function goes a little differently, we have 9 minus x squared y minus y squared. 9 is a constant term. With respect to y. In the second term, the x squared minus x squared is a constant factor. It's being multiplied by the y. We take the derivative of y and come up with 1, and we're just left with the constant minus x squared. So that's why we have this minus x squared term here. The derivative of minus y squared is just minus 2y. There's no x to confuse us. We're taking the derivative with respect to y. All we have is a function of y. Are we even dealing with a function of two variables? Here we have those two derivatives. Any questions? The other thing that I wanted to point out with this particular example is that I wrote find zx and zy. We can use our subscript notation, our new prime notation, our subscript notation with variable names too. We don't just have to restrict that to functions like f prime. We used to be able to write y prime as the derivative of y when y was a function of x. We can write zx and zy to be the partial derivative with respect to x and with respect to y, just like before. How's everybody okay? I didn't even have to tell you that was what I was asking for. So I wonder if that means the same thing as like y prime meant. Yep. Predictable. But we don't want to be unpredictable for the sake of being unpredictable, right? Because then you get to the end of the movie and it's like, oh, the butler did it. And he was never a character in the movie. That's like the dumbest ending ever.
This movie,
I don't know. It's just, that's an old joke. Not an old joke, but an old trope to make a surprise ending. All right. Let's suppose I ask a different question. Variation on this question. I haven't told you what these mean. I am making you guess as to what these mean. And you have to guess why there's 4 things that I want. I want zxx, zxy, zyx, and zyy. So please take a minute or two and find these 4 things that I haven't even told you what they are. Guess what they are, then find these things. So what are these four things? What am I about to call them? What comes after first derivative?
second derivative.
Second derivative. These are second derivatives. Why are there four of them?
There's fluid, liquid.
What's that? It depends on which variable you're using. We have two variables running around, so we have two derivatives. If we have two first partial derivatives, then each of those first partial derivatives has two second partial derivatives. So there are four possibilities. So these are second partial derivatives. I didn't even have to say it. It just looks like what you would do. This is the four versions of y double prime. Y double prime, we only had one of them because we got away with prime notation because it was functions of a single variable and life was easy. Life is even easier now because we get to use more variables. That's what made Calc 1 and Calc 2 so difficult. Everything had to be in terms of one variable. We only got to use one variable. Now we get to use two variables. So the partial is z with respect to x, and then again with respect to x. We'll just start here, take the derivative with respect to x, and what will we get?
Negative 2y.
-2y, the minus 2xy. Y is a constant factor, just like -2 is a constant factor. The derivative of x is 1, so we just get -2y. What's the derivative of -2xy with respect to y?
Negative 2x.
-2x. In this read, we're looking at -2x. X is a constant factor because we're starting off with zx. Now y is the variable. So -2 is a constant factor. X is a constant factor. The derivative of y is 1. So we get -2x. What's zyx? -2x. So this function minus x squared minus 2y, when we're taking the derivative with respect to x, derivative of -x squared is -2x. The derivative of -2y with respect to x, that's a constant term, and the derivative is 0. And what's the partial with respect to y? -2. Any questions? You already knew how to do this? Man, this class is going to be easy if you already know how to do all the stuff. Let's have the final tomorrow. That'd be kind of an awesome way to do things. Just give the final on the first day of class. And if you pass, then you don't have to come the rest of the semester. It's like, oh, you know enough.
We automatic for.
Yep. But then what would happen? What would end up happening is that you would like prepare for the class that could teach you all the shit by like learning all the shit from some book somewhere. It's like, oh, how do I pass this test on the first day so I don't have to do the class? And you just like spend all this time getting ready for the test when you could have just taken the class. And then, you know what? Just take the class. But people are like, oh, no. This way I feel like it feels different because you're like, oh, I feel like I'm getting something out of this. You know what I mean? Anyway, if I just set and if I just set up the class like, oh, you don't have to come to class, you just have to take a final exam. Then at the end, you'd be like, oh, the teacher didn't teach us anything, man. We just made it take the final. But if we just reversed that and gave you the final on the first day and said, if you pass this, what I'm saying is that students are weird. Y'all are weird. Your mind works in some very strange way that I should understand because I was a student, but I don't think I do understand because I turned out of a student and into a teacher. So, and we all know that that instantly means I become out of touch. I don't know. Just one of those things. All right, that's it for today. I will see you all on tomorrow. Everybody have a good day, and thanks for playing.